All right, so now how do we prepare our epoxides? So there's one way that we already talked about, which is using a peroxy acid. Remember, these have the generic formula that's generic formula RCOOOH, right? We got these three oxygens in a row. These are peroxy acids. These are great for forming epoxides from alkenes, right? So we learned about this in chapter 8 along with our alkenes. Again, one of the most common ones is this MCPBA, and I want you guys to be able to recognize this reagent here because I know for a fact that it's often on the ACS exam, okay? It is a peroxy acid. It is the generic formula like this. It's just a particular one that's very commonly used. To be honest, I have no idea why. I'm betting because it's fairly cheap to make and store as well, and all those other good things that make it a good reagent. But any peroxy acid would do. Again, be sure to recognize what MCPBA does. And again, that's to create an epoxide from an alkene. Remember, these are stereospecific reactions because they are syn additions. Hopefully that's fairly obvious as to why it's a syn addition, because, how are you going to create like a trans epoxide? But that does have, or, an epoxide where its bonds are on different sides. But nonetheless, it has different stereochemical implications, right? So if I took a cis alkene and reacted it with peroxy acid, I would get a different product than if I took a trans alkene and reacted it with a peroxy acid, right? Here, the difference is going to be the stereochemistry of these stereocenters here. Okay, so the fact that this is a syn addition is really important to the stereochemistry of the products. There's actually another way to make epoxides as well, and that is starting with a halohydrin. Remember, we learned how to make halohydrins starting with an alkene, kind of messy. And then if we added bromine in the presence of water, we would get this anti-addition of the two and create what's called a halohydrin, right? Turns out that if you take a halohydrin and you treat it with a base, what you're going to get is an epoxide. Okay, so let's see the mechanism for this. It's actually kind of cool. So what do we think is going to happen when we treat our halohydrin with a base? That base is going to do what bases do and deprotonate that alcohol. That lone pair is then going to jump on to that oxygen and create this alkoxide type ion. Now, what's going to happen is an intramolecular SN2 reaction. Intra meaning within the same molecule. This oxygen is now going to reach over and attack that neighboring carbon that's bound to that halogen, right? And then kick off that good halogen leaving group. If you want to look at it in the chair conformation, let's sort of see how the the conformation is going to be sort of key here to creating this syn addition product. Notice that you have to have this trans halohydrin should it be locked in a ring, right? If it's not in a ring, it doesn't matter because you can always rotate around that single bond. But if you are in a ring, you'll only get these types of reactions with the trans halohydrin. And then that creates this new bond, kicks off that halogen leaving group, and now creates this new carbon-oxygen bond, giving us our epoxide. Okay, so this is another way to generate epoxides, going through a type of reaction we already learned about, right? Those halohydrins. These will form the same exact products, these two methods. So starting with a given alkene, you will get the same product at the end. Okay, there's no sort of difference between these two reactions, whether you decide to use one in one case or one in another. To the best of my knowledge, there's no difference between the two, no matter what your starting product is. Importantly, again, would be that the stereochemistry of the product is going to be the same, right? So if I started with a cis alkene, I would get this sort of syn addition, same sort of product as if I were to use the halohydrin pathway as well. right? Which again would be different than if I started with a transalkene, right? These are stereospecific reactions. Stereospecific reactions, where that becomes really important is when you form, or where it becomes especially important, when you have these two new stereospecific that are produced, you will get then a racemic mixture of two different products. Notice that these are only two of four. Well, I guess you couldn't possibly have the other two diastereomers. So nonetheless, so yes, you would get a racemic mixture here because you would have addition from the top, right? Remember that these alkenes are flat, right? So I can have my addition, my syn addition happen from the top. That would give me one epoxide type product, or I can have my syn addition from the underside of this plane, and that would give me the other addition, right? So I can get this racemic mixture of two different epoxides when I create those two new stereocenters. All right, so again, let's just do a summarize here in terms of mechanism. You do not have to know it for the peroxy acid. It forms those weird cyclic things. It's actually in the lecture slides from chapter 8, but I don't want you guys to spend any time memorizing that. You should absolutely, though, know it not only for the second step of these reactions, the formation of the epoxide, but also remember you're supposed to know it for that first step too. So that halohydrin formation from an alkene. So yes, make sure you have the mechanism all the way through, starting with an alkene, going all the way to an epoxide for these halohydrin type synthesis. Regioselectivity, even though these are addition reactions, you actually don't have to worry about it, fortunately, because you're forming the epoxide where the bonds are always going to be on the same side. So it's not as consequential. There's no, the one thing I guess that should be noted is in this first step here, the OH goes on more highly substituted. So for those ones, if you were just doing the halohydrin, if I asked you for the mechanism, you would want to make sure that you paid attention to the regioselectivity of that first reaction, where the OH group is going to wind up on the more highly substituted carbon. But then once you do the next step, the regioselectivity doesn't really matter. Okay, but still for the mechanism, if I ask you for a mechanism, you would want to know that. And then lastly is stereoselectivity. And these are both going to be syn additions.